Okay, so our last and final talk is by Himanshu Gupta, who is a professor of computer science at Stony Brook University. His current research interests are in shared spectrum management and quantum networks. He graduated with an MS and a PhD from Stanford University in 1999 and has been a faculty at Stony Brook since 2001. So Himanshu, please take it.
Hello. Hi. Thank you, everyone. Thanks to speakers. So I'm Himanshu Gupta. I'm glad to be here. So I'll talk about the work that we did, creating a wireless link for the wireless, for the virtual reality headsets. We call the system Cyclops. This is with some of my students and colleagues. The students have graduated since, so I'm giving the talk. The work was done at Stony Brook University. All right. So we all know what a virtual reality headset is, so I'm not going to get into that. So our first thesis is that for a true lifelike experience, an immersive experience, the wireless headset should actually be wirelessly connected to the renderer. So that's the first thesis, so that the user can move around for a true lifelike experience. And the second is that this link should be able to support tens to hundreds of gigabits. There are claims or theses about even terabits, but I think 10 to hundreds is very easy to justify. Even a normal 8K stream with 90 frames per second and with 40 bits per pixels comes to around 120 gigs. So these are very standard rates, and the FPS can easily be much higher, and the resolution can be much higher. So you can easily see it goes to hundreds very easily for a raw data stream. So our whole work is based on the thesis that FSO is the right technology to create such a link. Okay, and let me just introduce briefly what FSO is. FSO essentially is you can look at it as a laser link, or essentially it's using light waves for wireless communication. The light waves, generally, the waves that are used for communication are in this range of 780 to 1600. Our work, generally, we use 1300 or 1550 nanometer because those are the devices that are easily available with the best specs. The key advantage of free space optical communication is that they are high-frequency waves, high-frequency, and it is easy to create very narrow beams. So that essentially facilitates very high data rates. There have been demonstrations of long links up to terabits per second. And the other advantage is that the spectrum is unlicensed. Okay? The key challenge that arises, and that is a challenge essentially we handle during this work, is that if the terminals move, then it requires a very precise realignment because the beams are very narrow. That's basically the fundamental challenge that we will across. Just a brief mention about other technologies. There are other technologies that may seem competing, but actually, in terms of being able to provide desired bandwidths at this point, they are likely not feasible. OK, so this is our setup. So we envision that the transmitter is fixed on the ceiling. So it's fixed. The transmitter doesn't move. And the user is wearing a headset with some optics, and I'll get into a little bit of detail on that. And so there is a FSO beam that from the renderer to the receiver. Now the user moves, so the beam is essentially misaligned, and we need to come up with a way to align this beam. Okay, so to realign the beam, we need to first localize the user. So that is fundamental, right? Because we need to essentially point the beam back to the receiver. So we need to relocalize the user. Now, the key here is that we need really millimeter level accuracy. And the reason for that is that the movement tolerance of the link that we have designed is essentially a few millimeters. And so we need essentially localization at the level of millimeter level. And there is a localization system inbuilt in the wireless, virtual reality headset. We are going to build upon that. That is, we're going to leverage essentially the localization that is inbuilt in the wireless, in the VR headset. So that is how we localize the user. And then based on this location, we want to essentially steer the beam towards the user. And therein, what we do is essentially we will get into detail on this pointing function. So there is a pointing function that takes in this location And what it does with the location is it creates what is called steering voltages, which will feed into the galvo mirrors that is part of the optical assembly. And that will essentially steer the galvo mirrors to point to the user. So that's basically the entire setup that we have. Now here, what we really need to address is how to estimate this pointing function. That's basically the key challenge of the entire work. And I just want to give a brief introduction to galvo mirrors. Galvo mirrors essentially are, we use two-axis mirrors, which essentially have a capability to steer the beam in a certain direction based on the voltages that are applied to these two mirrors. So each galvo mirror takes a pair of voltages, and there is a cone within which it can steer the output beam. So we have two of these galvo mirrors, one at the receiver and one at the transmitter. And so we essentially need to convert a VRH location to 4 voltages. Just one point I want to mention that here there is a need, because of the arbitrary angular movement of the user, that we have to also steer the receiver, the RX mirror also. Just steering the TX is not sufficient. OK, so we need. So the last few slides is going to focus on how do we estimate or learn this pointing function very accurately. So this pointing function essentially is a function that takes in an input, the VRH location, and outputs this 4 GM voltages. Okay. One thing I want to point out is this VRH location that we have is in an unknown coordinate system. That is, this VRH localizing itself for its own purposes, but we don't know where the origin is. We don't know what the orientation of this origin is. So it's an unknown coordinate system. That adds to the challenge. OK, so the first thing I want to mention is learning this. Of course, one can imagine learning this P function directly, blindly, or directly by collecting a large number of this input-output samples. But this is infeasible because, firstly, collection of each of these samples takes a couple of minutes. I'm sparing you the details, but takes a couple of minutes. And by our estimation and our preliminary analysis, it could take years or decades to gather sufficient samples to be able to get millimeter level accuracy. So our approach is an indirect way of learning the pointing function, which essentially involves looking at details of what affects it and learning one of the key components of this pointing mechanism, that is the GM. So we will actually offline learn the GM model, the galvo mirror model. First, in a known space, in a known coordinate space, then we will map it to the VRH coordinate space, which is essentially what we want eventually, because everything is in the VRH coordinate space, the location is in. So we will first learn it in a known space, then we'll map it to a VRH coordinate space, and then we will use these models to actually compute P in real time. OK, so that's basically our high-level approach. And I have 3 slides for each of these three points. So first, how do we learn the GM model? At a high level, we look at the physical configuration. OK, first, the GM function. GM function, essentially, the way we model the GM function, what we are trying to learn is it has an input of the pair of voltages, and the output of this function is the output beam, or the specification of the output beam, which can be represented by the originating point on the second mirror and the direction of the beam. So that is what we want to learn. How we learned essentially is we look at the nitty-gritty details of the physical configuration of the GM, and we basically create an expression that relates the input to the output, and then we learn the unknown parameters. That's basically the high-level approach. So that is the input and the output, just to make it very clear. And we essentially derive an expression, not a closed form, but essentially a sequence of assignments that essentially gives you an expression for this G function. But that expression is parameterized. It has all these parameters that are shown as a part of the circle. And we essentially, our job is to learn these parameters accurately. And the way we do that is we learn these parameters by collecting a large number of samples, by collecting some training data. I don't want to get into details of that, but essentially it involves placing a grid-like board in front of it and trying to hit the beam and each of the grids and recording the voltages, et cetera. And with that training data, we can actually estimate the parameter values using a standard optimization technique. So that is G. We also want to learn another function which helps in doing the in being able to estimate the pointing function. The other G is kind of a reverse function, but not exactly an inverse. So essentially what it does is it maps a target point to the voltages. So that is, given a target point, the goal is to compute the voltages that'll generate a beam that'll hit the target point. Okay? So this essentially does become essential for the eventual task of learning the pointing function or estimating the pointing function. This, we don't need to do any learning. We can actually use the G function iteratively to estimate this. Now to map it, so the previous slide talked about how to learn this GM function. Now we need to map it to the VRH space, which is unknown. With a bit of insight, one realizes that this is essentially tantamount or equivalent to learning the GM's positions in the VRH space. So that essentially boils down to learning 12 parameters, six parameters for each of the positions. And the way we do that is, essentially we collect some sample data. And for each of the sample data, essentially the sample data is a combination of voltages that aligns the beam. So we have basically VRH position for that particular position and the 4 voltages. So that's an example of a sample. We collect a few of these samples, and then we define an error function that essentially tells you that for a given parameter values, what is the error at a particular sample, which essentially, getting into a little bit of a detail, for a given set of parameter values, we can actually compute the beams that these parameter values will generate. And the misalignment of those beams gives you an error for that sample. So if you collect a large number of samples, you can actually compute the total error for a given set of parameter values. Then the goal becomes that what parameter values will minimize the total error for the collected samples. So that is a parameter estimation problem that can easily be solved using some standard techniques. We actually use third-party software to do the last part. So now we have the GM models in the VRH space. Now this part actually becomes easy now once we have that. So to go from pointing from the GM functions to pointing function, what we do is, again, recall for the pointing function, the input is the VRH position, and we want to output the 4 voltages. And our approach is essentially we start with some voltages, initialization, and then we essentially compute the output beam from the transmitter based on the given voltages, and that use that originating point as a target for a beam, for an imaginary beam from the receiver. That actually gives us, using the reverse function, that actually gives us better values for V3, V4. That is the values of V3, V4 that will actually hit the target point. Okay? And we can do essentially the same thing to compute new V1, V2 values. So essentially, we start with initialization. We recompute the 4 voltages, and we iterate until the error is minimized. That's essentially the estimate. And this is the only step that happens in real time. The previous 2 steps actually happen offline before the user starts using the VRH. OK, so now I have a couple of slides on the evaluation that we did. So 2 things. We designed a link in this setup. And then after designing the link, we essentially moved the receiver around in certain ways. And we measured what level of speeds the system is able to tolerate. I want to just, OK, I'll mention that in the next slide. So here, so we created links for 10 and 25 gig using the laser transceivers that are available off the shelf. And one thing that we did here was that instead of having a purely collimated, that is a parallel beam, we actually found that a slightly diverging beam has better movement tolerance because it essentially allows for a little more movement of the receiver without losing the link. So this is the setup. There is a transmitter which has the standard components, the GM, et cetera. The receiver, actually, we put it on top of, so the receiver includes, of course, the VRH and the collimator and the GMs. We put it on a rotation stage and a linear rail to be able to evaluate extensively purely angular and purely linear motions in addition to an arbitrary motion. Okay? And this was actually a stepping stone as to how we could actually evaluate the system and get the system robust performance. So there is essentially one evaluation slide I want to show you, which essentially tells you or shows you the high-level what we achieved, essentially. And this is for the purely linear and purely angular motions. The paper has more evaluations for arbitrary motions. But this actually does show what I want to show very clearly. That is, so here there's a time scale, and the blue is actually the speed by which the system is moving linearly, and the orange is the throughput received. So here we saw a very clean observation that if the speed is low enough till a certain point, for in this case up to about 35 centimeters per second, then we get optimum throughput. But as soon as the system starts moving beyond 35 or so, the link is lost. So that essentially tells you there is a movement speed tolerance. And this is actually the desired speeds that we want based on the user studies that we did. Similar for the angular movement also. And the paper has more plots for arbitrary motions where we actually do both, but therein we are not able to control the linear and angular so nicely. So one point I want to make is the performance can be much improved with customized components. We were severely limited by using the off-the-shelf components. In particular, what will help the most is a VRH localization with a much higher tracking frequency. So that is one of the very limiting factors. In conclusion, all I want to say is that what we have done essentially shows that FSO is a feasible technology for a high bandwidth wireless link for virtual reality headsets. Thank you.
Questions? So I'll ask.
Sure.
First. I was wondering how fast these mirrors move.
Oh, they are extremely accurate. They are actually very expensive, too. They are about $2,000 a piece, each of them. How fast they move? Their stepping by step is that a very small angle. I don't remember the exact angle, but it's in microseconds.
So is that why like,
Microseconds.
when you go to above 35?
No, that's not the reason. No.
Okay.
GM speed is not the factor at all.
Okay.
The main, there are multiple reasons why the system fails for a higher speed. Fundamentally, and that's actually will require getting into a lot of detail. Fundamentally, what is limiting is that there is some time, yes. So GM latency could have been a limitation, but that's actually very small. It's actually 1 millisecond. What limits is that we are getting a location update every 10 to 15 milliseconds. That's actually very high. So basically, for 10 to 15 milliseconds, we are kind of blind. So during that 10 to 15 milliseconds, the receiver is moving. So there is a delay in lag. So you're essentially fighting against that. That is one of the limiting factors. But the other, essentially, is the latency of this whole pointing mechanism. But that is the main component of the latency. Okay, the GM latency is about 1 to 2 milliseconds. Computation is less than a millisecond. Everything else is just 1 to 2 milliseconds.
I have one more question.
Yes.
So if you were to take into account what the user is doing, like how, if
Predict.
you know, a priori that like the user is walking in a straight line or the user, would that help?
I seriously doubt it. The main reason and the core of the challenge in all of this is we want millimeter level accuracy. So that prediction I cannot imagine it to be of millimeter level accuracy.
I see.
That's basically the fundamental reason. Because the user there is a movement, right? There's a 3-degree movement, right? He's moving his head a little bit, right? That essentially is very, very. And that is why we had to use the VRH localization system, because it does have a millimeter level accuracy. And creating something, a localization system, we didn't get into that. Yes.
Nice. Any other questions? OK, so we're already 15 minutes into the break, so let everyone go. If you have questions, the speakers are here. Thank you again. And the next session will start in 14 minutes.